Hello, I'm Dave Soriano, Associate Professor of Chemistry with the University of Pittsburgh's Bradford campus in northwestern Pennsylvania, USA. We're located in the Chem Department here, 300 Campus Drive in Bradford. And you can reach me at soriano@pitt.edu. This is a brief introduction to my current research involving synthetic diesel fuel oxygenate additive research. I'm conducting this with some of my students here on the Bradford campus. A good diesel fuel oxygenate, according to the current patent literature, should cut down on particulate matter. You envision adding 1 to 4% by volume of a diesel fuel oxygenate to conventional petrodiesel in order to enhance combustion and cut down on tailpipe emissions, the black soot, particulate matter, which among other things contains incompletely combusted hydrocarbons. One way to do this is to add compounds that contain oxygen in the structure to enhance combustion. Currently in the United States, such a fuel additive for gasoline oxygenate additive is ethanol. So current research is going on with diesel fuel oxygenate additives, as evidenced by a cursory review of the U.S. patent literature applications in the last few years. Now, a good diesel fuel oxygenate should satisfy several criteria. Number one, it should be economic as possible to produce. It should cause minimal environmental and health problems in case there's a spill. You don't want to put something into the diesel engine that's going to kick out an exhaust component that's worse than before. The candidate oxygenate should have as many oxygen equivalents per mole as possible. And of course, here at our school, we're finding that if we try to incorporate too many oxygen atoms, then we run into solubility problems with the petrodiesel. And that's the next point. The oxygenate should be as soluble in petrodiesel as possible, particularly at typically low operating temperatures found in the northeastern United States in the winter. The oxygenate should have a boiling point we have found of about 190 to 220 degrees Celsius. In other words, you want to ideally come in at the lower end of the diesel cut versus the higher end. And of course, you need to have, among other things, correct viscosity and acceptable flash point for storage and transportation. And you want to have minimal solubility in something like water, of course. Now, one approach that we're taking here at school is to prepare candidate diesel fuel oxygenates via 1,3,5-trioxane. Please note in this slide we have simtriazine. You would certainly not want to use that. You'd be incorporating nitrogen. No, we mean 1,3,5-trioxane. And we also use paraformaldehyde. React it with the alcohol of choice. In the case of this situation shown here, 1-pentanol, and currently researchers in microbiology are starting to prepare so-called biopentanol. We treat the 1,3,5-trioxane with 1-pentanol in the presence of a Lowry-Bronsted acid, and up until recently we've been refluxing that for 2 to 3 hours. At that point, we distill off any of the water that has formed and any excess alcohol, and then we vacuum distill the corresponding dialkyl acetal. In the case of 2 moles of pentanol reacting with the masked formaldehyde, the 1,3,5-trioxane, you would expect to get 3 moles of a C13 equivalent. This molecule contains This structure contains 2 oxygens, and it's a C13 equivalent if you count the oxygens in the chain. Now, we have been developing this process and modifying the process as we go along. An older approach that we used was to utilize ketal or acetal exchange, and in the case of triethyl orthoformate, you could make orthoesters, but if you simply want to look at the production of simple acetals or ketals, you would take the acetal, in this case with H, or ketal with R, and react it with the alcohol of choice with acid catalyst and do an acetal exchange. And we've been looking at using diethoxymethane, the diethyl acetal, of course, of formaldehyde, with 1 pentanol, 1 octanol, and the branched Guerbet alcohol, 2-ethyl-1-hexanol, to prepare C13 to 19 equivalent chain lengths in the petrodiesel range. Now, this research we've put to the side because we've developed better processes. A typical reaction, very easy to do in a fume hood, a bench scale. We use a pack column, glass column, to prepare the acetals, which, of course, the process you could find in any introductory organic chem book. That's the purpose of this research, to make compounds as efficiently simple as possible, the process. We get clear liquids, and an added plus is that they, as acetals do, they generally have very pleasant smells. In the case of triethoxy orthoformate, we've made formate orthoesters, and they are not as stable to hydrolytic conditions as acetals or ketals. But nonetheless, we have found that we can produce derivative orthoesters, but you do have to watch any water around, because here we're running an FTIR, and you can see that in the corresponding orthoester we produce, that you will get some hydrolysis. Now, we've left some of these orthoesters in water overnight at ambient temperature, and that's not too much of a problem. But for example, if we take the tri-N-pentyl orthoester and bring it up to 200 degrees Celsius, we will begin to see as much as 15% ester formation due to hydrolysis under those stringent conditions. We've been basically sticking with the production of simple acetals, but we do have some of these orthoesters going on as well. This was a first batch that we made actually just yesterday. That would be the 22nd of February 2012. This is a dipentyl acetal, a quick scan, very pleasant colorless liquid. And this is, of course, made from the 1,3,5-trioxane or paraformaldehyde. Typical view of nice colorless synthetic diesel fuel made from renewables, and of course the paraformaldehyde, a polymeric source of formaldehyde. Formaldehyde can be made from methanol technology, which in turn comes from natural gas, but the alcohols we're using are renewables, such as the biopentanol I mentioned. Here's a batch that we just made, a little better view of the material. So that is a reaction just carried out with paraformaldehyde, excess alcohol, catalyst, acid catalyst, and indeed, interestingly enough, going through organic synthesis, collective volume 1 of organic syntheses, first experiment that you find published in volume 1 is acetal formation at room temperature. So what we've actually been doing is carrying out acetal formation at ambient temperature by simply mixing the paraformaldehyde, 1 molar equivalent, with 2.1 molar equivalents of the aliphatic alcohol of choice. We charge in there anhydrous calcium chloride, and we place in there an acid catalyst. You can use your paramethyltoluene sulfonic acid or concentrated sulfuric acid. We then seal it up and we shake it. Please catch that typo there. We shake the reaction contents every few hours for 2 or 3 days, just leaving it in the bench top. And then we follow up by doing a vacuum distillation after decanting the acetal, the crude acetal, from the hydrated calcium chloride. And we distill to get the product oil, and we also get it away from the acid catalyst. So we cut down on energy input. So basically, this is the type of research we're doing with our undergraduate students here. I'm putting this in the open literature because I would like to share this with people working in the area. Please feel free to contact me. But once again, production of aliphatic acetals, aliphatic orthoesters. We actually analyze the tailpipe emissions using our stationary diesel engine generators. We have GC mass spec and capillary GC, and we're able to put these additives in as we prepare them at the 1 to 4% level. And our plans are to go up to what I would call a B20. And by B20, I mean the renewable acetal or orthoester in lieu of conventional biodiesel. So we like to think of this as possibly a second generation biodiesel approach. Thank you for listening. You take care. Bye now.